Welcome, everyone. My name is Obinna Amalu. Um, I am here to talk about actually, the name of my talk is Write Fast, Read Now, the role of persistent storage in real-time monitoring. So this all stemmed from a project that we worked on a few years back, and it all boiled down to the role persistent storage plays, especially software-defined storage in computing as a whole. So in this problem statement all comes from the human need for things right now. So in monitoring, in a manufacturing plant, for example, which is our area of focus in this use case, is in manufacturing. So in manufacturing, you want to detect defects instantly, quickly, to avoid problems down the line, right? So what does this imply? Writing fast and reading now means can you do those two should I call them tasks? Those two tasks, can you perform them almost simultaneously to give people the data they want? We're humans. One of our biggest traits is lack of patience. We already know that. When you go to get your food from a fast food restaurant and they're taking too long, you get impatient. I paid for it, I need it now. So that's the whole premise here. So what does this mean? Our use case focuses on Google Distributed Cloud Computing, which is Google's Edge platform. It's still in its refining stages. It will be GA soon, but I was fortunate to work on a project that used that platform to host a Kubernetes cluster that managed a real-time monitoring platform for a manufacturing company. So what does that mean? It means that when you're designing with the mindset of real-time monitoring, you have to always think about data. Data is key. All your manufacturing equipment, they spit out large volumes of data in very split seconds. How can you process? So I'll give you a good example. A scenario is one of the situations we were working on was a machine was spitting out 12 gigs of data per second. How can you process that in real time and give me a dashboard that depicts what's happening in near real time? So we started with the problem statement of we're running this in the cloud. The bandwidth cost is expensive. The cost of storage is expensive. The latency is too high. It was taking about 35 to 40 seconds to process that data. So what did we do? We looked around and figured out that, hey, something could work, which is persistent storage, but software-defined storage, hence Rakuten. So the integration of Rakuten into the Kubernetes stack was amazing. So on initial deployment, what did it do? It just simply took our whole 35 seconds and crunched it down to about 9 to 10 seconds. This was without any configuration, nothing of any sort. Oh, yeah, thank you. So what we did was we had an appliance, which is the Google Distributed Cloud connected. It came with 6 nodes. Each of those nodes had storage on them. But the thing with that is you can only use local disk mode in this method because let me start this way. Has anybody heard of Google Distributed Cloud Connected? Boom, boom, 2. So we have some not so strangers in here, right? Okay, so if you're familiar with it, you understand how it works. It does not understand the concept of anything persistent storage. You have to use local disk. So the only way to get persistent storage to work is to use Robin, which is Rakuten Cloud's software-defined storage solution to help with this situation. So on 3 of the nodes, you have the Robin master service running on it. Then all the nodes have the data service running on them. So the first 3 nodes can be used as master nodes and also as service nodes to handle data orchestration and all of that. So now you have your storage pool, which is the physical hard drives on each of those nodes, each of the 6 nodes. Then you have your application pods, and the application pods, when you set up replication during your deployment, you can tell it, hey, do a 3-way replication. So they have different storage classes also in Robin that can define how you want to replicate. So back to my problem statement. We wanted to achieve close to real-time monitoring, basically sub-second, right? The only way to do it was this was the only opportunity we had to play around with Rakuten Cloud storage, and it was a perfect synchrony. So we took that solution, deployed it as it was. We went from 35 seconds to 8 seconds. So on talking to Rakuten, we now realized that there was a way to patch the storage class to allow us work in low latency mode. So Rakuten also gives you that opportunity to work in that mode. So what we did was, when we deployed the patch, it took us from 9 seconds to 0.8 seconds. That was a significant, almost 85 to 90% reduction in latency for how we got, that was how we were able to get this to work. So the stack behind was Kafka, Prometheus, InfluxDB, and Grafana for depiction of the KPIs. So if you think about it, 12 gigs per second, and it was giving you back a response sub-second. That is a significant shift from 35 seconds on the cloud to 9 seconds without tweaks, and adding the low latency flag to your storage class. It took us to less than 1 second. So we were able to get things in a row. So part of the whole situation here was, in certain industries, let's use manufacturing once again, but semiconductors, for example, you do not want anything to run past you. So things are always caught, things should be caught in real time. Also, you want to be able to do predictive analytics with the amount of data you're getting. So you want to use the same platform, the same storage, and everything with all the data in it to be able to detect faults in real time, to be able to give real-time insights into the progress of your manufacturing plants and your whole processes as a whole. So this was one of the ways we went around it. So as I said, you have multiple storage, multiple replication modes. You can do a three-way replication. So in case node 1 goes down, you still have your data in node 2 and node 3. And you can, once you bring this back up, everything synchronizes. You can also go with one replication. If it dies, pray to God that you have your data somewhere, or it's gone. So we also have, so you can see all the, in the key here, you can see all the replication strategies there. So some of the key features of Robin is its easy integration to Kubernetes. So in the GDCC stack, when you're deploying it, it deploys the stack and it deploys CRDs for Robin, which is Rakuten Cloud storage. It deploys the CRD, so it's a seamless integration. You just have to enable the storage classes and make it your default storage class for it to use that replication. Before I proceed, any questions? Oh, you can use it for, it's not specific to Google. You can use it for GCP, you can use it for any, it's just a software-defined storage. No, you can use it for AKS, GKS, EKS, any of the KSs you want to use it for. But the aim is all about latency in this use case. So in this use case, it's all about latency. In other use cases, it could be, how do you manage your storage? So because of that orchestration layer where it sits above your storage pools and helps you manage your data efficiently, it's more about data optimization. If I use that word, it's how do you optimize your data reads and writes? That is why that's why it was a good solution that we selected. Sometimes also, because of how these platforms are designed, there are limitations. In this case, in the GDCC case, it does not talk back to Google Cloud, as you already know. It doesn't talk to Google Cloud. What it does is it uses certain services in the cloud, like GCR, which is just a bucket, artifact repository to store your artifacts, your containers and all. But the rest of it, you have to self-manage, like databases. You can't use Cloud SQL. You have to build your own Postgres or MySQL, messaging queues. You cannot use like PubSub. You have to build your own Kafka, and it's a specific version of Kafka, Streamzy Kafka. That's what works. So those are the only edge cases around. It's too cliche, but it's the edge case around edge computing is that it's so specific to the tool sets. So you have to find something flexible enough to provide that storage class that you need to operate the whole cluster.
When you go to me, this is very, very relevant. Are you around here later?
Yeah, I'm here.
I'll come and find you later.
Okay.
It'd be really good to have a chat.
All right, cool.
Cheers.
So, in some of the work we've done, these are the four most common use cases for edge computing and persistent storage because of the nature of transactions. So in retail, let's use McDonald's for an example. McDonald's is notorious for telling you their servers are down, right? If you have an edge node that has persistent storage that can withstand intermittent data fluctuation, it knows that once connectivity comes back, it syncs all the data to the cloud or wherever you want to store it. The good thing is now you can keep processing transactions because all your applications have been refactored, reconfigured to work in offline mode. And that's the key here, is how can your data persist through connection ups and downs. It's a use case in retail. In manufacturing, like I've been talking about, that whole real-time monitoring, real-time visual into your manufacturing end-to-end pipelines. In telecom, 5G, you can just spin up a mast somewhere and supply connectivity to people around because of edge computing. So all of it all sits in the edge platform. Also, air gapped. For example, if you're working in high security environments like government, state level, manufacturing, DoD, you do not want that data. Or in Europe, where there's the whole data sovereignty thing, where you don't want data out of Europe, but you want to have access to your data, but you don't want it leaving. GDCC is a good platform. So that's why the air gapped concept comes into play, meaning it's shielded from connectivity outside. All the data stays local, but you can still use it within your processes and your application stack. So that's the whole concept of the entire write fast, read now, is how can you perform those two processes simultaneously and keep it within sub-seconds or real-time monitoring. So I look at real-time like anything less than a second, to me, is considered real-time. That's the reality we have to face until something else comes out and says, no, that is no longer the benchmark for real-time. Real-time is right now. But in this case, right now is anything less than a second.